Started to talk about Lagrange multipliers. We want to find, we wish to find yes, the extrema of some function f under the constraints where gi is 0. We started the example, for example, as far as I remember. Did we start? No, just write it down. So let's start an example. For example, where is it? Just a sec. Here I'm using already examples I've already done before, but with all the variables and constraints and so on, and something that can be solvable in a reasonable time. So something like no, what did it teach? It was a test. Final example. Last semester B. You can. I believe in you. Oh, is it? For example, f of x, y, z is x squared plus y squared plus z squared under the constraint. It's just one. We'll do an example with two today. X squared above a squared plus y squared above b and z squared above c is one where a is greater than b, greater than c, greater than 0. For example, not just the experiment, but under the specific constraint here. So one can, of course, move the one to the other side, becomes g equals 0. How do we do it? How we find the suspected points by solving the following system. First of all the conditions of the constraints in the first part of the system. And secondly, the gradient of f should be a linear combination of the gradients of constraints. Why is that? I mean, we're not getting into that. I can geometrically explain it, but not now. We don't have time required. And for finding, then we calculate the values of f at the suspected points and find which of them is the maximum, which of them don't just find the maximum and the minimum, find the extreme. So let's do two examples. What? Okay. So first of all, example we've already written. So we can write, as I mentioned, g equals 0, just moving one to the other side of the equation. It's important to say that it's not necessary. I mean, this way or that way, we look at the derivatives of gi. So a constant Doesn't really matter. I just think it's more convenient to know that always should be equal to 0, but it's not important. So we need to solve the following system of equations.
Sorry.
Yeah.
GI are the different first, the first order partial derivatives.
No, GI is the constraints. I mean, here in this example, we only have one of them, so I just write in G and that's all. But sometimes we have G1, G2, G3, more than one condition. We try to find the extrema under these conditions, under these constraints. And in the second example, we'll have two constraints. You can see it more clearly. So the system of equation is actually containing four equations. Write it down explicitly. First of all, or lastly, it doesn't really matter what you write down, the constraint itself, and then the derivatives of f should be linear combinations of derivatives of g. Now there's only one g, so derivatives of f are some multiplication by this mysterious lambda of derivatives of g. Now lambda is called the Lagrange multiplier. One can say it's an assisting variable, something like that. We don't really need to find it. We actually do when we're solving the system of equations. It helps us find the xyz of the suspected points under the constraint. Of course, even though we don't need to find it exactly, we do need to observe that there is a solution. I mean, if we don't find it specifically, but one equation becomes lambda squared is -1 or something, then the xyz we found are not actually a suspected point. In our specific case, what do we get? The derivative of f by x is 2x, and of g by x is 2x above a squared, and it is similar for the other variables, just y with b. And z with c. Um, then we can write it down. Let's see. Looking at the second equation, we have 2a squared x is 2 lambda x. And then divide everything by 2. Move it to the other side. Let's take x as a common factor, and it is 0, which means menace, which means two options. X is 0 or lambda is a squared. Yeah, it looks fine. The third and the fourth equation are similarly solved. Similarly, we have y0 or lambda is b squared from the third equation, and z is 0 or lambda is c squared from the fourth, so, with the u, of course. Or not. Yeah.
So the gradient is the sum of...
Is the vector, it's not the sum. So what is written here, it's actually an equation between vectors, which means equation between each and every coordinate.
Yeah.
So it's actually three equations in this specific case.
Yeah. So it's the vector that you can represent as the partial derivatives of each variable in the place of in the vector, right? So
Yes.
So that's why you're doing fx equals
Gx, gy, gz. Right.
okay, and it's the same eigenvalue.
It's this, yeah, not eigenvalue. It's the same letter lambda, right? We call it Lagrange multiplier. It's the same one. Yeah.
Okay, and you're derivating g, or are you derivating the original? I mean, it's the same in this case,
Yes, because the difference is only a constant between equals 0 and equals 1 or something.
but it always has to be a constant. Yeah.
Yeah.
Okay. Why 2x over a squared? It's
The derivative of g. That's g. Straight g, homie.
now okay. What are we trying to do here when you have two different functions?
First, the one function is the function we're trying to optimize, finding the extrema. And the second one, or sometimes more than one, our second example, we'll see two of them, is the constraints. Is the constraint. Trying to find, and it's very common in reality. And every constraints we come from our computational limitations or something like that. We're trying to find the extrema in this closed region, not for every point in Rn.
So the constraint is just like the distance to the point?
Specifically, in this specific case, the constraint describes an ellipsoid. This equation describes an ellipsoid. So we look at the function inside an ellipsoid, and we ask in this ellipsoid, not in all R3, in this ellipsoid, which point is the maximum, which point is the minimum of the function given here, a different function.
Like because of the different variables under the different.
Yes, if it was the same A in the denominators, it was a sphere. Yeah, it was a sphere. Okay, so each equation gives us two options, which combinatorically speaking is actually 8 options, right? So we have 8 cases. Let's see. First of all, if x is 0, y is 0, and z is 0, we get a contradiction from the first equation. It doesn't comply. Doesn't, yes. First equation. Oh. Leads to a contradiction. Okay, second case, let's say lambda is a squared and y and z are 0. What do we get here? In this case, when y and z are 0, the first equation, when y and z are 0, leads to x squared above a squared is 1, which means that x is a or minus a, and we get the points plus minus a, 0, 0. Similarly, cases where lambda is b squared and x and z and are 0, and where lambda is c squared and x and y are 0,
Are they mutually exclusive?
Yes, there's different cases
No, I mean,
that solve the system.
yeah, I mean, but can it be b squared and c squared, or do the other words have to be zeros?
Let's see. Let's see. These cases lead to the points, expected points 0 at plus minus b 0 and 0 0 at plus minus c. The same way. The case of lambda equals a squared y 0 z 0 leads to the point and plus minus a squared 0 0. Now, of course, when we have the, let's say, this third case, third type of case, where lambda is a squared and lambda should be b squared and z is 0, we have a condition about a and b and c. They have different absolute value, which means that lambda cannot be a squared and b squared simultaneously. So it is a contradiction to the condition a greater than b, greater than 0. I mean, 2 is greater than minus 2, and nevertheless, they have the same square number, but where they're positive on one hand and one is greater than the other on the other hand, it cannot be the same lambda. Similarly, the cases of two of them is lambda and the third one is 0 leads to a contradiction, lead to contradiction. So it's B and C, it's 0. And the first kind of type of options is basically the same. Where OH of the equation is solved by the lambda. Again, contradiction. So, in conclusion, we have 6 suspect points. The values of f at this points are, now remember that f is squared, squared, squared. Let's, you know what? Why shouldn't we copy and paste it? So at plus minus a, we have a squared. We got this parenthesis. At b, we get p squared. And at c, we have c squared. Now we know that a is greater than b, which is greater than c, which is positive. So, and finally, in conclusion, the points of plus minus a give the maximum of f, which is a, while the points with plus minus c give the minimum or the minimum, which is c squared, by the way. So it's a squared, of course. One cannot visually show it because 3 dimension at the domain requires an additional one for the function itself, and we cannot imagine 4 dimensions. But we can think of the equivalent problem with two variables. It's an ellipse, not ellipsoid. It's basically the same. Any questions about that? So I want to do another example with two constraints. What the hell is that? No, something with, what is this? No, it's disgusting to write down. Sammy, specifically in this specific case, the constraint, the G, is an ellipsoid, like a football ball, yeah, like a football. But generally speaking, it can describe many things, not necessarily geometrically. I mean, it can describe some physical limits. We have some financial limits, trying to maximize my profit, knowing that I cannot overpass a specific amount of my budget or something, and so on. I'm looking for an example that will, give us good, nice numbers. So give me a sec. I mean, I did it last year, but I'm not finding it in the notes. Probably was in the classroom, written down on the board. So blah 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 blah. Into two. Okay. Okay. Is it? I have it. Another example. So it will be 2. The function f x y z is minus x plus 2y plus 2z. Under the constraints, g1 of x, y, z is x squared plus y squared minus 2 to be 0. And g2 is y plus 2z minus 1 equals 0. Here, geometrically speaking, the first constraint, G1, describes a cylinder. I mean, in the plane, it's just a circle, but here you can have whatever Z you want. So it's a cylinder, infinite cylinder. And y plus 2z minus 1 is a plane. And when a cylinder is intersected with a plane, it's probably an ellipse or a circle, something like that. The I mean, Sammy, just like, first functions of one variable, I want to find the extrema of some function f in a specific segment. So the constraint is a, b, x axis between a and b. Here we have different type of constraints, but it's basically the same. trying to find the extrema of a function, not for every point in Rn, but for every point that satisfies the conditions G1, G2, G whatever equals 0. The mathematical slang, we call it constraints. So it's not that the function f is under the constraints, it's more of the domain is under the constraint. Not every point x, y, z, but every point x, y, z that satisfies these conditions. Yeah, something like that. Something like that. Okay. Here the system of equations contains 5. Trying to copy exactly what we need to copy. It's containing 5 equations, and first of all, G1 is 0 and G2 is 0. And then fx, we have 2 g's here, so we need to use 2 lambdas, is G1 by x plus lambda 2 multiplied by the derivative of G2 by x. And the same goes for y and z. Copy, paste, change, repeat. Okay, G1 is this, and G2 is that. F by x is minus 1. G1 by x is 2x. G2 by x is 0. Not complaining. A good sign to save it. It's Infi 2, lecture 24. Okay, f by y is 2. G1 by 1 by y is 2y. And G2 by y is 1. Fz is 2. G1 by z is 0. MashaAllah. And G2 by z is 2. Okay. We need yet again to solve these single equations. It's not necessarily linear. It is not linear in this specific case. So Niebuhr would say, according to the eye, לפי העין, what seems the best way for you to solve it? I mean, the fifth equation gives us lambda 2, for example. So we find lambda 2, we move on. The last equation yields that lambda 2 is 1. Okay. It gives us the following system of 4 equations. Do I delete row call? Like that. Okay, we can write it as 2 lambda 1 multiplied by y is 1. Now we can, for example, sum the last 2 equations. In linear algebra, we write down as, R3 plus R4 lead to 2 lambda x plus 2 lambda 1 lambda y is 0. So taking out lambda 1 as a common and dividing by 2 leads to lambda 1 is x plus y 0, and we have two options. Lambda 1 is 0 and x is minus y. Lambda 1 is 0 leads to a contradiction. 0 equals minus 1 or 0 equals 1, so we can delete this. Let's do semicolon. Lambda 1 equals 0 leads to a contradiction in the third and fourth equation. So we are left with x is minus y. Okay, excellent. We can take x equals minus y to the last two equations. What do we have here? Oh, well, now x is minus y or y is minus x, whatever. First equation is 2y squared minus 2 is 0, which means that y is plus or minus 1. For y equals 1, we have x is minus y, so x is minus y, and by the second equation, y plus 2z minus z, z plus 1 is 0, and y is 1, so we get that 1 plus 2z minus 1 is 0, which means that z is 0, and this expected point is minus 1, 1, and 0. What do we get for y equals minus 1? Copy, paste, and change. For y equals minus 1, we have x is 1, and this equation means that 2z is 2, which means z is 1, and the expected point is 1, minus 1, and 1. Considering I'm not
Point can be minimum and maximum.
the same point.
I mean, not at the same time. They could be either without checking.
Yes. Actually, more than that. We mentioned Weierstrass theorem last week, the theoretical theorem that assures us we have an extrema, maximum and minimum. So whatever equation we solve, we need to find at least two suspected points. One to be the maximum and this one to be the minimum. We can find more than in the first example, we found 6. But we need to find at least 2. And we have, and we finished that. Solving the system of equation. We're finished, and we just need to calculate the values of f at these points. In conclusion, we have two suspected points, -1, 1, 0, and 1, -1, 1. The values of f are, again, in this case, f is -x plus 2y plus 2z. We have 2 points. F of -1, 1, 0, and f of 1, -1, and 1. Okay, at -1, 1, 0, we get 3. At 1, -1, 1, we get -1, as far as I can see. Now, in conclusion, the point -1, 1, 1, 0 gives the maximum, which is 3, and the point 1, -1, 1 gives the minimum, which is -1. Okay. Any questions? So I move to the very last topic in our course, the yes, integrals. Now, in integrals, we will discuss. I may mention from time to time what to we do when it's more than two variables, but all the examples and stuff will be about two variables. Um, first of all, the first part of the first of all, we only discuss we are discussed we only discuss definite. There was this discuss definite integrals. The final answer is a number. Okay, now the function. It can be a parameter if question has parameters, but it is a number. Secondly, we do not go into the rabbit hole of defining integrability here. It can be defined, but it's not simple as taking little segments, is taking little pieces of n-dimensional domain. So it's even uglier. We do not go into the rabbit hole of defining integrability. And thirdly, the properties of definite integrals of one variable functions, we discussed in lectures 5 and 6. It was extremely fun, of course. Can be generalized to the multivariable integrals. Specifically, that's right, specifically. Oh, wonderful. It looks weird to me, I don't know. Specifically, the integral, double integral, okay? Of f over some domain D describes the volume of the body, uh, third-dimensional body, three-dimension body, enclosed between the graph of f under, yeah, and above the xy plane. I mean, for my extremely good abilities of painting, we have some domain D, and we have some graph of function f above it, something that is three-dimensional. Now we can discuss the area, the volume of the body and close between the graph and the function. For example, it's probably better. Let's say I have my phone and the domain is the table. So what is the volume of the body enclosed between the phone and the table? Just geometrically speaking of the basic properties, but all the same properties. If f is greater than g, the integral of f is greater than the integral of g, and linearity, and so on and so on. One can write them down explicitly for multivariable integrals as well. Now, the problem, secondly, first of all, secondly, the problem with multivariable integrals is usually the domain. Functions are going to be cool or easy or something like that. We may need a little substitution, or an integration by parts. Let's write it down with a semicolon. Or an integration by parts. But the main problem, the main goal is successfully dealing with the domain we want to calculate the integral of f above. So we first discuss the a rectangle domain where x and y are both bounded with numbers, and then we will start probably continue in our last lecture on Tuesday. We'll discuss what do we do when the domain is not a rectangle. In the domain, we start with rectangular domains. Rectangular domain. So we can calculate the integral of f above a domain D, where D is a rectangular domain, meaning that x is between a and b, and y is between some c and d, in one of two ways, whatever we want, in the following ways. So one can start with x and then move to y. Let's use a parenthesis here. Or we can start with y and then move to x. Of course, so as usual, are you right? Usual? Maybe.
Singular.
I think 11. Okay. Looks weird. As usual, when we integrate by one variable, we consider the other or the others more, but as I mentioned, we actually discuss only two variables, unlike the other topics in multivariable calculus here. We consider the others to be a constant. Okay, for example, let's calculate the following integral. I don't know. Integral of x squared y plus y third. And now for a notation in the integral itself, one can use ds or dA or d whatever. I mean, the integral without the d is weird, but it's not really important. Where d is a rectangle where x is between 1 and 3, and y is between 0 and 4, whatever. Let's, for the sport, do it in both ways and be extremely surprised when we get the same result. Let's start with the first option. We'll first calculate integral by x and then by y. Now x is between 1 and 3 and y is between 0 and 4. So f is x squared plus y third. Now, integrating by x, considering y to be a constant, the outer integral is 0 to 4, and it is x squared y above 3 plus y third x, where x is 1 and 3, dy, whatever we get here. x is 3. So we have 27y above 3 plus 3y third minus where x is 1 is y above 3 plus minus y third on dy. Let's organize it a little bit. It's 26 above 3y. Maybe wrong, so correct me. And 2y third. And we know how to calculate this integral. Integral is 13y squared above 3 plus 2y to the power of 4 above 4. At 0, everything is 0, which is extremely nice. And at 4, we get something. And as far as I can tell, that is a number. No, yes. It's revelation. Shocks me. Let's write it. I'm using Wolfram to tell you what it is, so we can see that in the other way, we will get the same. Plus.
Is there a whole theorem of why you can change them?
Yes, I will refer to it later. Well, he claims that it is 592 above 3. He may be or maybe not correct. Okay, any questions? So let's do it the other way around. It's another example. We'll see that, it is the same. Another way, we can use the other way around. There, first calculate the integral by y, and then calculate the integral by x. So the integral by y is x squared y squared above 2 plus y 4 above 4, y 0 and y is 4. So for 0, everything is 0. Putting in 4, you get 4 squared is 16, above 2 it's 8, 8x squared, and 4 to the power of 4 is 256, above 4 we are left with 64, and yet again calculating this integral for x is not hard. It is 8x cubed above 3 plus 64x. For x is 1 and 3. Okay, so for 3 we have 8 multiplied by 9, which is 72, plus 64 multiplied by 3. For 1, minus because it's uh, um, the lowest limit. It is 3 above 8, minus 64. And asking Wolfram again. 72 plus 100, no, 182, minus 64, minus 8 above 3. It is, how surprisingly, 592. Both three. Want to learn some infi?
Sure.
Want to start infi? Want to do argazim in the high-techs? But you're late for that. אתה תיכוניסט?
Yes.
אז יש עוד זמן. אל תדאג אבל. מה עם אימונים לצה"ל? איזה שנה אתה? איזה שנה אתה? אז מה עם צה"ל? מה עם אימונים? כבר קיבלת דברים?
כלום.
אתה צעיר עוד או למה?
לא, אני רגיל, לא... לא נהייתי טיוב, פניתי לגמרי, לא עברתי.
יש לך משהו ספציפי שאתה רוצה?
לא.
בסוף, בסדר? לך 3 שנים, תראה קצת ברובה, תחזור, יהיה בסדר. בזמני זה היה, אקדמיזציה זה היה מסלול טוב. היום זה כבר פחות. לא תנאי כמו פעם. Any questions about that? Okay, so, what the hell? Sweet. So,
זה לא קצת ככה.
that's all. It was your idea. We can't study like that. What did they?
לנו צד השני.
Maybe, but it was the second class, wasn't it? Last week. This one? No. No, I think it was the.
If that's it, then I was fine. Take care.
So just generally speaking, we know that when it comes to integrals, the calculation part can be much harder and uglier than derivatives. One can think of examples in which one way of calculating is pretty easy and the other one is pretty hard, even impossible, because the function does not have an antiderivative, or at least an elementary antiderivative. We will see an example like that, but not on rectangular domains, but in more general domains. So you asked how can we know for sure that it is legal to change the order of integration. Switching the order of integration is legal by Fubini theorem. I'm not getting into the specific details without specific details. It is enough, but of course not necessary, is enough for the function to be continuous. Then we can change the order of integration, however we want. Now, the first interesting anecdote about Fubini. He was an Italian politician, such like that. They used to do many things in early ages. Now he's just mathematicians. He was Jewish, just like Sylvester. So the second Jew we see today, we see in this course, and it's the first and the only. Yes, we're already finished, almost finished. The first theorem from the 20th century. It's 1904, something, 04, something like that. I mean, it's already more than 120 years old. But it is from the 20th century nonetheless. Okay, we're not yet again phrasing it mathematically precisely. Just by Fubini, if the function continues, we can do it. So theoretically speaking, we can do it whenever we want. The problem is about the technical of actually technical part of actually changing the order of integration. When we move march forward to the second type of domains, we are willing to know how to calculate integrals above. I call it X domains and Y domains. X domains and Y domains. Um, uh, what, what, what is this? What is the meaning of this? Controllers. Um, a domain D, which is all the x and y in R2, where um x is bounded between numbers and y is bounded by some functions of x, is called X domain. It's my own name of my own. Above X domain, over, better than above, over such a domain, the only way to calculate the integral of f is starting with y and then putting the boundaries as functions of f, and whatever we achieve, we then calculate the integral by x. So in the bottom line, we finish with a number, as we mentioned before.
Only y is a function of x.
Where y is bounded between two functions of x. I mean, one of them can be a constant. And when two of them are constants, that's just our rectangular domain. But when y is bounded between functions of x, while x is bounded by numbers, I call it an x domain, and this is the way, and the only way, to calculate the integral. On the other end, or similarly, a domain of the form x is bounded between functions of y, and y is bounded between numbers is called y domain. Over such a domain, we can only use the following way. First, calculate or integrate by x, and then calculate the integral by y. Um, well, let's have an example. Let's calculate the integral over d of the following function. Same function for first example. I mean, why not? Why shouldn't we? DS or whatever, where, no, different row, different line, where D is the following domain, all the points that are 2, that satisfies x is between y cubed and y, while y is between 0 and 1. Notice that, for now at least, we know how to calculate integrals over 3 types of domains: the rectangular, an x domain, or y domain. Now, I'm not saying I'm going to ask you about it in an exam or homework, but giving an arbitrary domain, one can probably divide it to some subdomains, each of which is a rectangular domain or x domain or y domain. And just like in one of our functions, if we calculate the integral over all the subdomains and sum the results, we get the integral over the domain itself. So generally speaking, we actually know to calculate integrals over domains that are not necessarily X domains or Y domains or rectangular domains, but probably not going to SQ about it. Okay, so D is described as a Y domain. So we calculate the integral following way. Now X is between Y cubed and Y. And Y is between 1 and 0. What is the function? The function is this. Now we know how to integrate this function by X. It is X third multiplied by Y above 3X cubed plus XY cubed between Y cubed and Y dy. Now, putting in Y instead of X leads to Y to the power 4 plus Y to the power 4 minus X is Y cubed, gives us here Y to the power of 10 minus Y cubed. Y cubed is Y to the power of 6 without the limits. Yet again, we know how to calculate this integral. It is Y to the power of 5 above 15 plus Y to the power of 5 above 5 minus Y to the power of 11, 33 minus Y to the power of 7 above 7, whatever this number is, between 0 and 1. And at 0, everything is zeroing. And at 1, we get 1 above 15 plus 1 above 5 minus 1 above 33 and minus 1 above 7. Believe it or not, it is a number. An irrational one, which is
Yes.
nice. Yes. Can't argue with that logic. Whatever.
Is it even irrational?
What?
Is it even irrational?
No, it's a rational one. Irrational. Sum of fractions. Any questions about that? So now, yeah.
Sorry. When we have an integral, like a double integral, we always have to resolve the inner one before the outer one. Sometimes we can change the order, but we always resolve the inner one.
Yes, yes. Notation means that we solve the inner and then the outer, exactly. So now, for the first non-trivial question, how do we change the order of integration over such domains? One can ask, why should we? When we have a way to solve the integral. So, for example, looking at the following example, say, I mean, I've already have it here. The integral above d of e to the power of y squared ds, where D is the following domain, xy in R2, that satisfies x is between 1 and 0, and y is between x and y and 1. So D is described as what I called X domain. So by our, one can think of as definition, the integral of f should be calculated in the following way. A and v, f is the ey squared. Now the limits of boundaries of x are 0 and 1. Boundaries of y are 1 and x. Because of this little x in the domain, we think of it as an x domain, and the integral of e to y squared. And the problem is very clear. E to the power of y squared in the very first lecture, lecture number 1, 3 months ago, something like that. And we say that we do not know how to calculate its integral, meaning that it is, at least Elad is not familiar with an elementary antiderivative of this function. So we're stuck here. Now I promise that if we first calculate the integral by x, we can calculate the integral of this function by x, just multiplying it by x, and then, mathematically speaking, maybe we will be able to solve the integral we get, and I assure you, let me promise you, that we will be able to do it. The problem is that when it comes to an x domain, we cannot integrate it first by x and then by y, because we will finish with x, not with a number, as we desire. So the problem is not connected to integrals at all, actually. The problem is, how do we describe this domain D as a y domain? How do we change the way we look at this domain and write it as all the points where x is bounded between functions of y, while y is bounded by numbers? So, and we, let's write down, and we do not know how to continue here. In order to change the order of integration, we need to change the way we describe the domain D. Instead of x between numbers and y between functions of x, we need x to be between functions of y. One of them can be a constant, and y to be between numbers. So, it's not some very algorithmic process. You just look at the inequalities that define our domain and try to build them differently. Okay? We look at the inequalities. At the inequalities defining the domain, and we try to write them differently in a way that helps us. So here we have x is greater than 0, x is smaller than 1, yx is greater than y, and y is smaller than 1. So x is greater than 0, and x is smaller than y leads to x between 0 and y, which is not very difficult to see. From here, we have y is greater than 0, and with y is smaller than 1, we have y is between 1 and 0. So, what we got, ladies and gentlemen, we got them. The domain D is actually all the x and y, where x is between 0 and y, and 1 and 0 are the numbers bounding y. So, and now we can calculate the integral above D the other way. So changing the order of integration when the domain is an x domain or a y domain is actually change the way we look at the domain. The integral is just an extra in the show of the domain. So y is between 0 and 1, and it's between 0 and y of x is y. Let's finish this example, and we can go each one to his way. Now the integral by x is like a constant, so we multiply it by x, and we put the limits where x is 0 and x is y. For 0, it is 0. And for y, we get e to the y squared multiplied by y. A small difference, but one that changes everything. Where e is multiplied by y, which happens to be the inner derivative, we know that we know who is the elementary antiderivative. It is e to the power of y squared above 2, the inner derivative, where we put y equals 0 and y equals 1. So our final solution is e to the power of 1 minus e to the power of 0, which is 1, above 2. It's a one-liner, but we couldn't do it the way D looked at first. We have to change the way we describe the domain, and then we can, and pretty easily, calculate the integral. Okay. Any questions about what we did today? Class, Zoom, oh, just in time, started to mock us again. Okay, so we can call it a day on Tuesday. So last lecture, I hope to finish everything we need, but of course, something we will not study something that we want us to study, it will not be with the final exam, of course. And I hope we have some minutes to talk about final exam, just tell you about the structure and other technical data or data. Sammy, stay well.